everyone, and welcome again. We are in our last talk of the day. If you're just tuning in, we are at DevFest Algiers 2021, and now we're having our talk about distributed machine learning from an AI research engineer at InstaDeep, Azeddine Chenine. We are going to welcome him right away.
Hello, Misa. Hello,
Hello,
everyone.
Azeddine. Welcome.
Welcome. Good to be here.
Thank you for coming. Thank you for accepting this invitation.
I'll be always GDG, so
Of
I'm
course.
at home.
Azeddine Chenine is an alumni from GDG Algiers, and as we always say, GDG for once, GDG forever. Yeah. So, without further ado, I will let you go with your presentation, so you can start sharing your screen now.
Okay, you see my screen?
Wait, I think it takes a couple of seconds to show up.
Okay, maybe I'll let the team share my screen now. So if I reshare now, so 1 second. It's supposed to be on now.
Let's see. I'll just remind our audience that they can leave any questions in the comments, and we'll be taking them at the end of this talk. And
Okay, so you see my screen now?
yeah, it's working.
Okay, so hello again. So it's welcome to the DevFest. I welcome myself also to the DevFest. I've been here for 3 years, and I'm happy to be here again at 2021. So with you today is Azeddine Chenine, alumni at GDG Algiers, and currently working as an AI research engineer at InstaDeep, which is an AI startup. It's like international AI startup. So and we'll be talking today about distributed machine learning. So distributed machine learning, like it's a simple, not simple topic, but simple to understand and can be tricky to work with. And it's just machine learning in distributed manner. Our presentation today will be very simple. We have like 4 points to talk about. First, we will start with the limitation of centralized training and why and when you should consider distributing your ML workflow. We move to the distributed ML paradigms, where we can talk about different manner and the different ways you can start distributing your ML trainings. And we will move also to the references and how and where you can start your distributed ML journey, as same as I started, like, let's say 1.5 years ago. And we will finish up with the Q&A, and I welcome all questions, like personal question regarding career paths or regarding the presentation itself. So let's start. So we start first with the limitation of centralized training. And before hitting the core of our topic, let's start with some phenomena that we can observe. So the first one is that data is growing exponentially, like you see on the chart on my right. And we can take like real insights about this phenomenon. Like from Forbes 2013, they say that more data has been created in the past 2 years than the entire previous history of the human race, which is huge. And McKinsey in 2016 has another insight saying that, take for example the year you are living at, let's say 2020 or 2021 or 2016, like based on the insights. So you should be sure that 90% of digital data you have now has been created just in the 2 past years. And only 1% in fact is being analyzed. And 80% of this data will be unstructured by 2025. And by unstructured data, I mean the data that doesn't have spreadsheet, like sheet structure, let's say images, video clips, audio clips, text, etc. And it was done by IBM in 2020. So this unstructured data happened to work well with deep learning. So we observe another phenomenon, is that deep neural networks are exploding in size. So most of the current application of deep neural networks is unstructured data. You have translation, protein design, object detection, let's say, for example, self-driving car, etc. So all these applications handle unstructured data. And the more data you have, ignoring the algorithm you are using, the bigger your model tends to be. And we are observing this too, like with models like GPT-3, which are same as GPT-3, which are delivering extreme good results. Let's say, for example, Codex is a descendant of GPT-3, and it's powering the GitHub Copilot, which is the famous AI-based autocomplete tool, like we all know about, and it was really a breakthrough. And since 2021, 2012, scaling your model came with a cost also. Like the amount of compute needed to train these models is doubling each 3.4 months based on OpenAI. In fact, this 3.4 months doubling period is surpassing the Moore's law. Like since 2012, like 2012, computation has grown by more than 300,000 petaflops per second in a day. And by petaflops, I mean 10 to the power of 15 floating operation per second. This is a huge. And by comparison, like you see on the chart on the right, Moore's law had a 2 years doubling period. Like if you see the chart, you'll have discoveries that is doubling according to the Moore's law. Then past like 2010, you have new era where things just explode with VGG, ResNet, and AlphaZero. So the hardware designers are also killing it. They didn't sit back and let the ML models eat their infrastructure. Like if you take the NVIDIA DGX A100, for example, it's the world AI first system built on top of NVIDIA A100 GPU, is delivering immensely big powers. Like comparing with the P100 is doubling by 11 times. This is also more than Moore's law, more than the Moore's law that we discussed before. For example, we have 19.5 teraflops of floating point performance, 40 to 80 gigabyte of memory, 1.6 terabyte of graphics memory bandwidth. This is also huge. So what you can say is that if I am facing a challenging model in terms of size, I will just take my infrastructure and try to have a better GPU. And what you are trying to do now is that you are trying to scale up your compute. So let's say, for example, you take a GPU of P100 and you replace it with A100. Now you scale your throughput, memory, and number of CUDA cores. So basically, what we mean by scaling up your compute power is that you take what you got and you replace it with something more powerful. But this is also comes with problem. Machine learning on single machines can present also problems. For example, you can have such a big model that it can fit even in the GPU memory. And even if you have your model fitting into the GPU memory, you can have training batch size, giving experimentations that doesn't fit into your GPU memory also. And even if you have the 2-point checked, what about pre-processing your data? Maybe the amount of CPUs you need to pre-process your data in a fast manner can be hosted into a single node. And the most problematic thing is that what if your node crashes? What happens to your experiment? Like what is the failure tolerance rate in your system? Those problems can be handled by distributed machine learning. So basically what you are trying to do in distributed machine learning is that you take your training workflow and you try to distribute it to work in a faster and a more fault tolerance way. And I like to bring this quote by Elon Musk saying in Tesla AI Day 2021 that I invite you all to watch. In general, innovation is how many iterations and what is the average progress between each iteration. So if you can reduce the time between each iteration, the rate of improvement is much better. So even if you trust your algorithm, if you can make your training faster, giving your compute power, you can achieve better results because you have many iterations in fewer time. So let's talk about another concept that is related to distributed machine learning, which is scaling out your compute power. So instead of scaling up your compute power, which is taking your infrastructure and changing it, no. You take it as it is and you try to duplicate it and replicate it so it can work in parallel and handle all the loads you are getting to it. So next slide. So in machine learning on multiple machines, what you can do is that you provide your training workflow with multiple nodes. Let's say, for example, as you see on the right, 4 nodes. You can, for example, have your large model split it into different nodes, and we will see how you can do that, because basically linear algebra is parallelizable. So if you have, like, let's say, operations happening inside your training workflow, you can parallelize it. And this is what seems like easy when doing distributed machine learning on like distributed infrastructure. You can parallelize all the maths happening there. Or you can also take your dataset and split it across different nodes to have a fast pre-processing and like better I/O throughput. And also the most important thing is that fault tolerance strategies can be used to handle node failure. So if you have 4 nodes and you have one node is failing because of an issue, you can recover from that and rely on the rest, like the healthy 3 nodes. So now we'll start digging deeper into the distributed machine learning topic, and we will start with the paradigms. So the first way to the first option to do when you try to tackle this, tackle a problem related to the training and try to establish a distributed machine learning workflow. First, you try to parallelize your data. So basically, your data is partitions and as many times as there are workers in the node. And all the workers are working in parallel to handle your algorithm. And you are basically having the same algorithm, the same model deployed into the 4th node, for example. So let's take this example. Let's say you have a data set. So what you're going to do first is that you take your data set, you split it, let's say, for example, to 4 sub-data sets, and you replicate your model on each node. For example, here we have 3 nodes. So each node will take the same replicate of the model. And you will try to allocate for each worker the subset of your full dataset. So each worker will operate on a subset on your dataset using the same replicate of the model and the same algorithm. When a worker finish one iteration of your algorithm, let's say SGD, or stochastic gradient descent, it will try to communicate its, let's say, gradient or weights to the other nodes in a synchronous or asynchronous manner. So when you try to distribute your data, you have 2 options. Either you do it synchronously or asynchronously. And synchronously, we mean this thing. After all workers finish an iteration, the gradient or the parameters are reduced in a way that each worker tries to communicate its results to all the other workers. So when a worker finishes doing its one iteration, it will wait till the other finish doing their iterations and receive the results. It will be aggregated. Let's, for example, you take the mean of the gradient of all the workers, and you try to sync your model according to these results. This is feasible and implemented in many machine learning libraries, including TensorFlow. They have their own communication, which is similar to the ring communication, because you are basically having a ring of nodes that are trying to communicate to each other. But the problem with this is that you go only fast as your slowest worker. So if you have an heterogeneous infrastructure and you have, let's say, node with faster GPU and a node with slow GPU, the faster GPU will, when it finishes the one iteration, it will try to wait until the node with the slowest GPU finish its iteration also. So you will have what we call ideal GPU time. And the solution for that is to use asynchronous data parallelism, which we call parameter server generally. So the idea here is that you keep the same architecture as the synchronous one, but what you will add is that what we call the parameter server node, which is a simple node hosting the parameter of your model, and it can be only CPU. You don't need GPU for this. So the tweak here is that when a worker finish one iteration, it will push the gradient parameter or the parameters to the parameter server, where your weights are being hosted. When the parameter server receives the new weights that have been pushed by your worker, it will try to push back an update of these weights into the worker pushing these weights. So the parameter server will compute the new set of weights and push it back to the worker. Now your worker doesn't have to wait till all the workers finish their task. So the worker will only communicate with the parameter server. But we have a problem here, is that it is harder to tune, because like when you are working with the push-pull system, your worker doesn't wait for the other workers like to finish their iterations. So it can happen that, especially when you are working in in heterogeneous environment, like if you have a fast worker, it will have a higher push and pull rate than the other worker, which can be which can hurt the learning, and it will be harder to tune your hyperparameters and the push-pull rates. So like the learning, it can be even between all the set of workers. This is a challenging task also. So basically, like it's trade-off. It depends on your architecture, on your infrastructure, and on your model also, and on your hyperparameters. So if you want to compare like the synchronous and the asynchronous way to do this data parallelism, if you choose to go synchronously, you are as fast as your slowest worker. You will have ideal GPU's time, maybe, especially if you have heterogeneous environment. Workers need to communicate with each other. Like if you have, let's say, n worker, you will have n multiplied by n minus 1 communication link, which is like sometimes it's a bit challenging and present a bit of an overhead. On the other side, in the asynchronous type of data parallelism, each worker runs independently. So no matter what you're trying to add to your infrastructure, you have n communication. But it would be harder to tune, which is easy to do in synchronous architecture. So now you have trade-off that you can choose which one works better for your infrastructure and which one also works better for your model. So this is the first way to do distributed machine learning, which is data parallelism. If the other way to do data parallelism is model parallelism. And what we mean by model parallelism is that the model is split across workers. The exact copy of the entire dataset are processed by the worker nodes, which operate on different parts of the model. So when doing data parallelism, what you do is that you replicate your model, but you split your dataset. When you do model parallelism, you replicate your data, but you split your model. And like the famous article like discussing this type of architecture is the paper that handled the methods called disbelief. It was like called the large-scale distributed deep networks. It was published by Google Research, Jeff Teen, and other couple of authors. So let's say you see the image on my right. So you have a model split across 4 machines with 5 deep layers. And you see that each machine on the infrastructure take a part of these models. And it needs to communicate only the weights of the links which are bold. So if you want to explain this, so a 5-layer deep neural network with a local connectivity is partitions across 4 machines, the blue rectangle. Only those nodes with edges that cross partition boundaries will need to have their state transmitted between machines. So it's highly dependent on your model architecture. If you want to split it, the number of connections you may have with other machines depended on the way you want to split it. Like in this example, the first, the second, and the third layer of your deep neural networks is split across the 3rd and 4th machines. And the 4th and 5th layer is split on the first, like the first and the second machine. So the machine number 1 is communicating to machine number 2, number 4, and number 3. And it's the same for the other machines. So if we want to make a resume about this, computation for individual nodes will be parallelized across CPU. That's what has been done on this paper. So if you take one machine, the computation that is being done on one machine is being parallelized across the CPU on this node, because they use only CPUs. But the idea is simple. You take your model, you see your architecture, and you see which machine can take which part of your model. And it's up to you to handle the communication of the, let's say, the back propagation and the forward propagation. And this paper in general delivered very good results regarding the conversion, let's say the speed up, because they took speech image model with 80 million parameters and speech model with 1.7 billion parameters, and they really achieves good results regarding the speed ups in terms of machines per model instance. You see, let's take the image model with 1.7 billion parameters. You'll have speed up of nearly 50 regarding the number of machines used. So, do I need data or model parallelism? It depends on you. You choose data parallelism if your model can fit into your machine. And maybe you choose model parallelism if your model cannot fit into your machine. Because data parallelism is a choice when it comes to how fast you want your data set to be to be pre-processed or treated by your machines. And also on how much you want to scale your batch size. So if you can split your data set across many machines, it will be very easy to do that. But when it comes to model parallelism, it's a bit harder to implement. And to be honest, it's not that obvious, especially when using primitive machine learning functions. It needs some really difficult, don't want to say difficult, but challenging ways to implement it. So if your model fits into your into your machine, it's no need to go for the model parallelism. So the challenging about distributed machine learning is the linear scaling. And by linear scaling, what we mean is that model A training converts on single worker after an iteration, while performing at r iteration per second, takes t time. So if you have a model that will converge after an iteration and it's performing at r iteration per second, and it takes t time to converge, when you scale your infrastructure and use k worker, it should converge after t, it should converge after t divided by k time. So since you are parallelizing your workload, the convergence time should be t per k time. And when each worker reach n per k iteration, it should be performing at r multiplied by k iteration per second. So what we are saying now is that basically you will reduce the time needed to train. So you will converge at t per k time. You will have a higher throughput. So you have r multiplied by k iteration per second, because we are doing many k iteration in parallel at time. And also on each individual worker, you will need n per k iteration so you can converge. This is what we mean by linear scaling. And it's really visible on the right chart. So what you are basically saying is that when you scale your infrastructure, the speed up should match the scaling. But it's too good to be true, because the model convergence can present a challenge. What we mean by model convergence is that you need to preserve the number of overall iterations required for the model to converge while scaling. So if your iterations to converge is k iteration, you need to divide this k by the number of workers you are using. And it will be harder like to achieve because of it's hard sometimes to tune your hyperparameters, and it's harder also to tune your update rate, especially when we're working with asynchronous architecture. By training performance challenges, what we mean is that accelerating the rate of step execution while adding more workers requires minimizing the overhead of gradient sharing algorithm. So what we said, like the more you add nodes to your infrastructure, you need like to share your gradient in a synchronous or asynchronous way, and it can present really an overhead when it comes to synchronous communication. Like for example, the ring communication, the gradient reduce, and the parameter server communication, like communicating the push and pull weights. So these two challenges can be like handled with experimentation. You can experiment with how many nodes is perfect for your workload, because maybe when you scale your like infrastructure to many nodes, it can go the other way, like it can go sublinear rather than scaling linearly, which is perfect. So if you want to like talk about distributed machine learning in practice, the first reference is TensorFlow Distributed Training API, which is a really simple training API, like presented by the TensorFlow team, that has implementation to parameter server, to the synchronous training, and to other types of distributed machine learning workflow. You can check that. Especially, I recommend checking the TensorFlow Summit and the talk linked on the slides. And the other reference that I recommend is the paper by Jeff Dean called Large Scale Distributed Networks, which held an experiment training like deep neural networks with billion of parameters on 10,000 of CPUs, and we have already like saw the best the good results that it delivered. So it has really cool ideas about how to distribute your model across different machines. And also there is a good survey that I'm linking it here, talking about different distributed machine learning algorithm and the challenges that come with it. And finally, this is good also a Medium post about distributed deep neural networks, and especially what are the challenges that comes with linear scaling that I recommend. So thank you for listening, and happy to receive your question.
Thank you, Azeddine, for this awesome presentation.
Thank you.
We can take the questions now. So we have one from Zakaria. He says, what are the softwares used for distributed machine learning?
So, like when you try to distribute machine learning, there are multiple layers to that, like that process. What I am like capable to talk of is the software layer. So, basically, what you have now is that you have a hardware, like a communication in terms of hardware, and communication in terms of software. In terms of software, there are like really high-level APIs provided by PyTorch, TensorFlow, and we can also list JAX to do this distributed workflow. From the hardware layer, like mainly those like each node will be like Dockerized and has its own like the own resources, and you try to communicate like the results of each node with the other one, and it's mainly done by these libraries, and you don't have to think about it. And personally, I didn't went that deep with the communication between nodes.
Interesting. And how about that's a question more of a career-wise. As a AI research engineer at InstaDeep, what are the different challenges you face in your daily work?
So basically, what like when you try to scale your model so you can have like faster iteration, giving the same model because you have like a larger compute. First, what you will miss is that you miss the overhead happening is the communication. So although you are scaling your compute, you will go sublinear. because like most of the time you are like losing time when it comes to communication and it comes like to data splitting. So key challenges is that how to like implement metrics that not only give you how good your model is going, but also how bad is the overhead being like present on your infrastructure. Let's say, for example, you need like metrics about output, metrics about like GPU usage, metrics also about the time you are taking per iteration. So these metrics give you an idea about how good is your distributed like workflow being handled by your infrastructure.
So it's like a multi-objective kind of optimization problem. You need to optimize many frontier while developing to take into account this overhead, as you mentioned.
Exactly, yeah. And like it can be difficult to manage sometimes, but good metrics could lead you to like better insights and conclusion on your workflow.
Interesting, yeah. And how about the um, the different contribution you have with other AI researchers or other engineers within the team? Does this help knowing that perhaps you're using too much GPU, or does is there any communication that might help in reducing this challenge?
But like by communication, you mean exactly what?
With other software engineers that might deploy this development, or is it like one person that does the whole pipeline? You develop the distribution strategy and you deploy it, and then you can check about your overhead.
Yeah, like a good question. Like first, like things come especially from the MLOps guys, which will like set the infrastructure and all the Dockerizing workflow to be like handled at low level, and it's up like let's say for a research engineer to implement like the data pipeline and like the different mapping functions that would like treat each subset for data set, for example, in terms of like when you are talking about data parallelism. And basically those mapping functions are usually like handled by higher level API of TensorFlow or either PyTorch. So basically if you have a good infrastructure, it should already take into consideration that you can distribute your machine learning workflow. So it's mix between MLOps that would set your infrastructure to be like supportive to the distributed machine learning workflow, and also the research engineer to implement those higher level API.
I see, yeah. uh, I think that's all we have in the chat questions. Any last words you want to share with us about how's life is at working in InstaDeep?
So at InstaDeep, like Karim said, distributed machine learning is taking a large part of our work. Like we have already like open source open source libraries for doing that. Like I can say that Meva, which is handling the distributed deep reinforcement learning, and it's doing it like in a high specification because it's based on Acme. So I invite you to check this. But distributed machine learning is a key when it comes to faster iterations and faster conclusion on your experiments.
Thank
So
you.
we are doing do good at that.
It definitely looks like it's the future. So, yeah, thank you
Yeah,
for this talk. Thank you for answering our questions.
thank
And
you.
thank you for coming, for accepting this invitation.
Pleasure. Yeah.
So, this is our last talk of the day. And thank you for tuning in with us. Thank you for uh, putting your questions in the comment, for interacting with us. And we hopefully will see you soon. Have a great night.